All right, we are going to continue in this section working with three-dimensional shapes as they relate back to vectors. Today we're going to look at lines and planes in space. And I'm going to start by talking about the lines. As with lines in a plane, we can specify a line by identifying 2 points on the line. Or 1 point on the line and the direction of the line. So in 2 dimensions, when we talk about direction of the line, we're referencing what? Slope. Yeah, we're referencing slope. Unfortunately, we can't just reference slope in 3 dimensions, right? There's more to it than that. And in 3 dimensions, we have 2 ways to represent the equation of a line. Those 2 ways are called parametric and symmetric. So these are the 2 representations. So parametric looks like this. It actually ends up looking like we have lines defined for each one of them. So x is x1 plus a, I'll do it that way, at. Y would be, actually I'll do a1t. Y will be y1 plus a2t. And z is z1 plus a3c. Not z, t. I wrote t and said z, okay. And this is for a point x1, y1, z1, and the direction is a vector. So, and the vector A, which is, I'm calling it A1, A2, A3. So we have a point in this form, and we have a direction, namely a vector. This is parametric representation. The other representation is symmetric. And you'll see the relationship when I write it down. Symmetric form says I have x equals, not even equals, x minus x1 over a1 equals y minus y1 over a2, which equals z minus z1 over a3. And how or where would that come from if you're already considering the parametric form? Take them component-wise. if you take a look at this, how do you go from here to here? What's happened? You solve for t. And t is the same, right? T's, our parameter. It's the same in all components at the same time. So if we solve each one of them for t, then those are the three different equations that we would get solved for t.
So we can say all that equals t.
You could, yeah. But we use the symmetric equations notation sometimes, and sometimes we'll use the parametric equations notation. All right. So we're going to start by finding parametric equations and symmetric equations for a line. But we're going to do it given 2 points, because we referenced at the beginning, like this dialogue that I wrote at the top says, we find lines using either 2 points or points in a direction, a point in a direction. I've kind of shown you what happens when you have a point in a direction. We'll talk more about that in a minute, but let's start with what happens when we have 2 points. So we're going to find A, parametric, and B, symmetric, equations of the line through these points, 0, 2, 1, and 2, 0, 2. Okay, so our equations, that is the parametric and the symmetric forms that I presented on the previous slide, all hinge on knowing a point and a direction, and the direction is known as a vector when we're working in 3 space, right? So I have a point, I have a couple of points in fact. How do I find the direction or the vector that we're talking about? Got it. We're going to make a vector between these 2 points. So our direction or our vector can be found component-wise, just like we did early on in section 11.1 or whatever it was, by subtracting. So I have the second vector minus the first, second point, minus the first point to get my vector. So I have 2, -2, and 1. Okay, all I'm doing is component-wise subtracting this point minus this point. This is now our A value from what we did before, right? We called this A on my previous definitions and so forth, yeah. Right, so we should be able to find everything we need once we have that vector, right? So let's do parametric equations first. So x equals what? Well, it says x1. What's x1? It's 0. And then I need plus a1t, and a1 is 2. So this is 0 plus 2t, or just 2t. How about y? What is y going to equal? 2 minus 2t, and z? 1 plus t. So those are my parametric equations. How about my symmetric equations? The first one would be x minus 0 over 2, or x over 2, equals, what about my y's? Y plus 2 over -2. And, oops, this is equals, and our z part? I think it's supposed to be y minus 2 in the middle, isn't it? I have minus 2 on my paper, and I'm looking back again. I'm pretty sure this is a subtraction one.
It is.
Yeah. Okay, I think everything else is okay.
Yeah, that's where I was confused.
Okay.
Yeah, my bad.
Sorry about that. I was just letting you lead the way, Kyle. Man, leading us astray. All right, I'd like to show you a definition. Oh, did everybody get things written down? Sorry if I switched too quickly. We're okay. All right, definition. Let L1 and L2 be lines in space with directions A and B. All right, L1 is parallel to L2 whenever A is parallel to B. That makes sense, right? If their directions are the same, hence they're vectors, then the lines should be parallel. Second statement, if they intersect, so if L1 intersects L2, so if L1 and L2 intersect, then A, the angle between L1 and L2, we'll call it theta, is the same angle between A and B. Furthermore, B here, the lines L1 and L2 are orthogonal whenever A and B are orthogonal. So that's kind of friendly. We can take what we know about vectors and we can apply them to lines in terms of finding out if things are parallel or orthogonal. It all hinges back on the vectors that are associated with them. So for example, on this one we're going to determine whether the lines are parallel skew or intersecting. You know, in 2 dimensions, I know I've had a number of you in geometry, but in 2 dimensions, you don't have a third option. They're either parallel or they intersect. But in 3 dimensions, you have the possibility that they could be neither parallel nor intersecting. And if you think about our classroom, the word skew, if you think about our classroom, you can actually think about the sort of the corners of my classroom. So if you look at the line along the top where the wall meets the ceiling, consider that as to be a line. And you consider the line along the floorboards where the wall meets the floor over here. Those lines are not parallel, right? But they are also not intersecting. They're in different planes, if you will, and they can't intersect from where they are. So that's a third possibility that we might have. And if they intersect, we're going to find the intersection. So we're going to find the point of intersection.
So if the lines are parallel, doesn't that mean that we have some scalar component
Yes.
that each of them that we can
Yes.
parallel
Not with the lines, but with the vectors.
with vectors?
Yes, that's correct. So we're going to change all of this into vector form once we are considering which one it might be. So here are our lines. This is, I never numbered it, so I'll put the number here for 2. One of my lines is x equals 4 plus t, y equals 2, z equals 3 plus 2t. And my second line, and these are the parametric forms, is x equals 2 plus 2s, y equals 2s, and z equals -1 plus 4s. I've got all these equations, but these are really just 2 lines. Okay, 2 lines here. And Bryson's exactly right. We're going to go back and consider what do we know about the vectors that are the directions for these lines. So the first thing I actually need to do is I need to figure out what my vectors A and B are. So we will let vector A correspond to this first line, and vector B correspond to the second line. So if I'm looking for vector A, how can I find, or how do I find vector A from this form? We haven't done that yet. We would need to know what the t values are that are associating to make that work.
1, 0, 2.
And so how are you looking at that, Kyle? Because I think that's probably a bit more straightforward.
Coefficients on t.
Yeah, it's the coefficients of the t that we're looking for specifically. So the coefficients on the t, here's a 1, this one's a 0t, and this one's the 2, right? So it's kind of a mess. But that would be our vector. Our vector would be 1, 0, 2. And if we look at the second line and we look at its coefficients for t, I have what? 2, 2, 4. Okay, so if these are parallel, what would have to be true about my vectors? Yeah, one of them would be a scalar multiple of the other one, and they're not. And you can actually know very quickly that they're not. How come? Because that 0 that's in there, and it's not replicated in the other vector. Good. So continuing on then, they are not parallel because A does not equal C times B, where C is a scalar, right? And that there is no C for which that happens to be the case. Okay, so how do we find out then if they intersect? I mean, they could be intersecting still, or they could be skew. How do we assume for the moment that they intersect? If they were to intersect, how could we find the point of intersection?
Do you do the cross product?
Nope. Nope.
That product will see it.
It's easier than you guys are thinking of. That's okay. You actually were almost on the right track before, Hannah, but in a different reference point. You mentioned something about finding t, right? So what we're going to do is we're going to find, I mean, if they intersect, they have to happen at the same place, like they all have to hit at the same place of a t value. So let me show you what I mean. So we have x equals, what is it, 4 plus t. And this x value would have to equal the other x value somewhere, right? Well, my other x value is, 2 plus 2s. So that's not super convenient. In fact, I know that this is x equals, but I'm really interested in solving for it. Yes, that's what I'm going to go to next, you bet. This is not super convenient because t and s have a linear relationship. They're both present, right? One equation, 2 variables, I can't solve it. The y equation is easier to work with. So my equation for y on the left-hand side is 2. That's a constant, which is super nice. And the equation for y in the second equation is 2s. So this actually tells us what is s. It's 1. And if s is 1, I can go back up here and I can solve for t then, right? Okay, so if s is 1, what would t have to equal in the other case? It's 0. Okay, so t is 0. And the question is going to be that when I consider z, Well, those values for an S and T also produce two Z values that are the same. Do they not? What happens? Let's see. I have Z is 3 plus 2T. I think it does. It does in my notes, unless I made an error, which it could have. And I have negative 1 plus 4S. So if I put in T is 0, and I have S is 1, do these equal one another? They do. So the reality is, I didn't know that it intersected when I started looking for the point of intersection. And if it had done what you thought it had done, Kyle, then what we would have found, like if it didn't work at the end, I didn't get Z values that were equal to one another, then they wouldn't intersect. They just wouldn't. And so I would have skew lines. So I'm making an assumption that they intersect, looking for that point. If I find the point, they intersect. If I don't find the point, then they're skew. Does that make sense? Okay. So these lines are going to intersect. Where do they intersect? Where T equals 0 and S equals 1. So if I go back up to my equation here, and it doesn't matter, it shouldn't matter, right? If I've done it right, which equation I look at, and I let T equal to 0, or I look at over here S equal to 1, I'll find an ordered triple. And what ordered triple do I find? 4, 2, 3. They intersect at 4, 2, 3. So when,
know that they
oh.
don't intersect whenever C doesn't work.
Yeah, so if you are not able to find that ordered triple, and I mean, you could put these in matrix form if you got complicated enough messes and you wanted to use matrices. You're welcome to do that. But if you found, like in a matrix form, if some of your linear algebra, that you ended up something with where there's a 0 row in a row reduced echelon form, then that would be an example of one where you're not going to actually have a solution. And you have skew lines.
So do you have to do, when you're looking back at the solution sets, you have the scalars like plus T and the scalar plus S.
Yes.
Is that where you can just row reduce and throw those away, basically, to
Yes.
find your solution?
Yes.
Because you don't need a separate like vector column for those scalars to solve.
I am not sure, Bryson. I sort of said it in this sense that you can use the linear algebra to do it, but I haven't actually done one with the linear algebra because I didn't have one that needed it. I was able to do it with other pieces separately, so I'm not sure. Yeah, I'm not sure.
Right about the row
Yeah.
stuff.
Yeah, you would end up with something that wouldn't work in a row reduced form. All right, we like to three-dimensionalize things, right? So when we talk about points on lines, and we talk about lines in a plane, and then we would talk about planes themselves. Okay, so that's where we're headed next. These are planes in space. So a plane in space is determined by specifying a non-zero vector and I'm going to call it N. N has components A, B, C. I'm just following what your book used on this one. The reason we're using that N is because that N is normal to the plane. Have you guys heard the word normal before in mathematics context? What do you remember about it? What normal means? It means perpendicular, and we've also used the word in here as orthogonal, right? So specifically normal vector, or normal, means that it's orthogonal to every vector lying in the plane. okay? And a point. So it's normal to the plane, and a point x1, y1, z1 lying in the plane. Almost done, and we'll stop after this one. Its equation is a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. Or one more form of it is you could say that it's ax plus by plus cz plus some coefficient. It's a collection of all of these terms and these other basic, these other components in here, d equals 0. This is an equation of a plane.
Is that also the standard, like the parametric form?
Yeah, I mean, basically, yeah. So I think that the second one is what they call it, the standard form or something like that of a plane. Yeah. And we will pick up here online. You'll watch the rest of this online later.